Welcome back. Today, we'll continue with our discussion on two-dimensional NMR. I hope you are all with me. In the last couple of classes, I extensively discussed the need for a 2D NMR, varieties of pulse sequences are available, and information derivable from these pulse sequences, and the proper choice of a experiment for you, depending upon the size of the molecule, what type of experiment you have to choose, depending upon what type of information you want to derive, all the things I said. And I also said each pulse sequence has certain delays, certain pulse widths, certain flip angle, depending upon the direction in which you apply the pulse, depending upon the angle of the flip angle of the pulse, depending upon the delay you have given. By using spin physics, you can trace the path of the magnetization. You can understand what is happening to the nuclear spin. You can understand the behavior of the nuclear spin by knowing spin physics. Every time you cannot represent by a vector diagram, which we did simple for APT and inept like this. We have to adapt at a higher level mathematics called product operators, which is not going to be discussed here because it is an advanced topic by itself and I do not want to frighten you going into too much of mathematics. This course is aimed at showing you the utility of the 2D NMR and giving the conceptual understanding of many of the NMR 1 and 2 dimensional NMR concepts, experiments and their utility. So I do not want to discuss about those things, but I told you how we can design the pulse sequence. But another interesting thing which I want to tell you is in each 2D experiment, the relation between one or two spins within the molecule are established by what is called magnetization transfer. Because when two spins have to interact, there must be a transfer of spin polarization or spin magnetization. Otherwise, there is no interaction, right? Because of the interaction, we have to have transfer of spin magnetization, and it happens in any of the 2D experiment. This magnetization transfer mechanism is different for different experiments. If it were to be same, then only one experiment would have been there. So this is the beauty of NMR, where you can understand what is happening to the magnetization in different ways. What happens to magnetization, x-axis, y-axis, z-axis, whether it is in-phase magnetization, whether it is anti-phase magnetization, all those things you can understand by understanding magnetizations, how it behaves with different pulses, different delays, and which direction it is applied. So we can understand the transfer of magnetization, mechanism of transfer. So in most of the experiments, there are various ways. I'll highlight only some 2-3 experiments which you may need it. We do transient NOE. In this case, Z magnetization transferred via NOE. Magnetization along Z axis. This is transferred between two spins which are in close spatial proximity by NOE. That is one way. In the Z direction itself, Z magnetization itself will be transferred. Inept transfer. Inept we have discussed where polarization from abundant spins was transferred to less abundant spin. Here, antiphase to antiphase coherence transfer takes place. We saw what is antiphase. We observed that in the inept and APT case, carbon 13 2, this thing, one was minus, the other was plus 5. They were in antiphase direction. They were opposite each other. That can be done in inept using via J coupling. That is the antiphase to antiphase coherence transfer there. You can go to TOCSY, total correlation, another experiment which you discussed. Here, multiple in-phase to in-phase coherence transfer takes place. That is another interesting thing. Again, through J coupling. This is through space, this is through J, this is through J. There is a Rossi experiment. Again, NOE transfer takes place in this XY plane. Here it is a Z plane, Z axis. Here, XY plane, this is spin lock. See, transient NOE, steady state NOE, driven NOE, rotating frame NOE, varieties of experiments are possible. But I just wanted to give you one or two information about you. In all the experiment, there is a mode by which magnetization gets transferred. There is a pathway, there is a way in which magnetization is transferred between two interacting spins. This is essential. Otherwise, you will not get the required information. So, this is what we understand by spin physics. and then design the experiment. You can exchange the magnetization, polarization, transfer the polarization between antiphase to antiphase, in phase to in phase, in the XY plane, in the rotating frame, or in Z magnet, varieties of things we can do. Okay, these are the things, and based on this thing, number of experiments could be created, and it has been created, and with a called specific experiment like COSY, heteronuclear correlation, heteronuclear single quantum correlation, multiple bond correlation, NOESC, NOC, ROSY, TOXY, etc. All these things have been derived. If you go and understand the spin physics, the way magnetization behaves in this pulse sequence, one of these things you will find out or something different. Not only, I just mentioned only a couple of them. There may be several ways you can see how the magnetization gets transferred. Now, with this, I want to tell you one thing. The common homonuclear 2D experiments, which invariably you people use it for your analysis, are not all, but many of them. You can use COSY, phase sensitive COSY, double quantum filtered COSY, soft COSY, relay COSY, TOXY, inadequate. These are all the experiments. As we go ahead, one by one, we will try to understand. Whatever possible, we will try to do. May not be possible having time to see everything. And also we have NOC, J-resolve also we can understand. ROC, I don't think I have time. I may not be able to discuss these things in this class because NOC itself, we have taken 2 classes. Still, we have not been able to complete 2 or 3 classes we took. Still, lot more we have to do, and I abruptly stopped. We may have to come back again to continue further. That's a different question. Okay, so that's why I asked whatever is possible to cover in the remaining classes, I will try to do with specific example so that you get a feel for what is going on. Similarly, heteronuclear 2D experiments commonly used is HETCAR or COLAC. These are all outdated nowadays. I am going to tell you what we do in this case. Nowadays, nobody is going to use this type of experiment. To enhance the speed, we use inverse experiment. There is a relay experiment called HEHAHA, heteronuclear Hartmann-Hahn. In the earlier case, we have TOXY. It is called HOHAHA. That means homonuclear Hartmann-Hahn. This is HEHAHA, heteronuclear Hartmann-Hahn. So heteronuclear J-resolve. There are a number of such experiments possible. You can do that. Okay. So there are inverse experiments, which is very, very powerful and very popular. Nobody uses this HETCAR, COLAC, I told you, nowadays. This type of experiments are not used because they are very time consuming experiments. Of course, information you get similar to these experiments, but these are faster experiments. It saves lot of time. They make use of polarization transfer. What it does, take the abundant spins, take the magnetization from abundant spins, give it to carbon or nitrogen, no abundant spin, and take it back to proton. In this process, you will know what is happening to the dilute spin. You can indirectly detect the dilute spin by taking the magnetization from abundant spin, giving it a rare spin or dilute spin, taking it back to abundant spin. This type of experiments are called inverse experiment, where you detect the abundant spin. What is the advantage? Faster experiment. If I detect carbon, as I told you, we discussed about sensitivity. It is very, very less sensitive compared to proton. Nearly 5,800 we thought. Okay, 6,000 you take, no problem. 6,000 times less sensitive compared to proton. Whereas if I detect proton, it's easy. But indirectly I can get the information about carbon or dilute spin. That is the advantage. So these are all inverse experiment. Now it is commonly used. Nobody uses HETCAR, COLAC, such experiment. But they were designed, and these are all the extension of that, an improved version of that for speed of the experiment and to enhance the sensitivity. Okay. Now we will start a simple experiment called 2-dimensional COSY experiment. This is where we start with. This is simplest of the possible 2D experiment. Number of 2D experiments are there. This is simplest to understand, simplest to interpret the spectrum. You don't need to break your head at all. This has 4 time periods, as I mentioned, for any routine or general 2D experiment. This is called preparation period. This is the evolution period. Where is the mixing period here? I said there are 4 periods: preparation, evolution, mixing, and detection. This is the detection period. Where is mixing period? It is absent in this type of experiment. Or you can consider this small microsecond pulse for 10 or 5 microsecond 90-degree pulse you apply. We treat that itself as a mixing period. No problem. Doesn't matter. Or in reality, there is no extra time delay given. You can say mixing period is absent or call this delay itself as a mixing period. No problem. Okay. What is happening in the preparation period? We are preparing the spin system. What do you mean by preparing the spin system? In this example, in this type of experiment, you want to make sure nuclear spins attain thermal equilibrium. Put the sample in a magnetic field. Wait for some time. After some few seconds, and spins start aligning in the direction of the field or in the direction opposite to the magnetic field. Based on Boltzmann population distribution, they get aligned. Very simple. And we prepare the sample. This of course, this can be different. You can prepare in a different way for different experiment. No need. But in this example, I am taking preparation first, attaining thermal equilibrium. Next is COSY. I'm sorry. This is the evolution. Next is evolution. Look at the evolution period. Here we are varying the delay. Indirectly, I am creating a pseudo free induction decay, oscillating damped signal I am going to collect as a function of T1. When I increase the T1 as a function of time, keep on increasing the delay, then I keep on getting the FID, I collect the signal, and I am going to generate a pseudo free induction decay in the indirect dimension, which is also damping like exponential decay, similar to this. So we are in the evolution period, we allow the spins to evolve, and then we start detecting the signal. What happens here and here will come, I will explain to you later. And here we are going to detect the signal. And this is the simplest of the 2D pulse sequence, but in this case, both the pulses, what we apply here and here, are 90-degree pulses. These are 90-degree pulses. And there is no need to have this as 90. You can have COSY 45, varieties of angles you can have. You can have a small angle, small flip angle COSY. Varieties of things you can do. But in the first COSY experiment design, these two are 90 degrees. And this is what happens. Okay, I'll apply pulse, increment T1, collect data points here, collect data here, T1 data, T2 data. I have 2 time domain data. I'll do the Fourier transformation and I'll get 2 frequency domain signals. Fine. Now what do I get out of it? The thing is, this experiment establishes the connectivity between immediate coupled neighbors. Beautiful. That's what I said. If I have a molecule with CH3, CH2, there is another CH3, another CH2. Now consider this CH3. This is CH3, CH2 and CH3. I do not know whether this CH3 is connected to CH2 or this CH3. Whether this is next to it or CH3 next to it, I don't know. Of course, I know from the multiplicity pattern. Supposing it's a kind of complex pattern, I don't know. What do I do? This gives me connectivity information between immediate coupled neighbors. What does it mean? It must be a coupled neighbor. So J coupling is necessary. Without J coupling, COSY doesn't work. You need J coupling for COSY type experiment. Some coupling information is required. So when the one proton is coupled, for example, I take a CH3 here, and then CH2 here, and another CH3 here. Now I get correlation of this to this, this to this. I can say from the spectrum, this is its immediate neighbor and this is its immediate neighbor. Like that, I can start getting immediate connectivity information of the neighbors. This is a very beautiful information. It is like getting multiplicity analysis, which we do in the 1D, so that to know which is coupled to which. This is what exactly it is. Like I said, in the one-dimensional periods, we have to do selective decoupling to get connectivity information to see which proton is coupled to which. I said we need to do hundreds of such experiments to get that information. We don't need to do it now. One two-dimensional experiment gives me complete information of all connectivity information of all the protons which is coupled to H. I'm sorry, excuse me. So it is easy. Does it not simplify our life? Very easy to analyze. This is the most beautiful and the first experiment of the 2D. Okay. Now we'll understand what is happening in this Cauchy experiment. The magnetization in this case is brought back to transverse plane. This is all we know. This is a 1D pulse. If you apply magnetization which is along Z axis, will come back to XY plane, transverse plane. That's fine. Now here, what happens here? The spins which are brought to this transverse plane, they start evolving. Instantaneously they will be in phase, and then afterwards you create phase coherence, and after some time these spin packets start moving in different frequencies, fast and slow moving components. But during this time what happens, they start evolving as a function of chemical shift, as a function of their T2 relaxation, and if there is a magnetic field inhomogeneity, all these factors contribute here. All these things will make magnetization to evolve here, start evolving, okay, in this period. Then what we do is we apply a second 90-degree pulse. What this does, it transfers part of this magnetization to the longitudinal axis, because it is already somewhere in transverse plane. Part of it transferred to longitudinal axis, and part of it will be left in the transverse plane. That's what it does. Okay, it second 90-degree pulse transfers part of the magnetization longitudinal axis and leaves rest in the transverse plane. And finally, during this period, we acquire the signal. Here, the chemical shift is identical to that during this evolution period. It has evolved, and chemical shift is whatever the chemical shift was there for different spins here is also retained here, is identical. Okay. So now what we do, increment the T1 points and acquire a complete 2D data set in 2 dimensions. Vary this, fix this constant period, collect signal, keep on varying. Like you take full time domain data, complete time domain data by linearly incrementing T1. Of course, this incrementing you do linearly. You can also randomly you can vary the T1 and do in some experiments. Okay, we can also do that experiment, not T1, but in some mixing times we can vary the randomly vary mixing time and all those things. But in this case, in the T1 increment, it is linearly incremented in subsequent scans, so that you get a full time domain to a data signal. Time domain signal is mentioned as here, it is given S of T1 T2. Signal is S in both the dimensions called T1 and T2. You see that represent as S bracket T1 dot T2. That means you got the signal in 2 dimensions. Now do the double Fourier transformation, which I showed earlier. Then you are going to get the frequency domain spectrum in both the dimensions. That's all you are going to get. This is what experiment does. So now let us take the example of 2 spins which are coupled. How we get the peaks. Okay, this is what happens. But how one spin has a correlation to other spin. This gives you correlation information. What is correlating and how it does. I give you hand waving argument here. Please, there is a detailed mathematics to understand this. You have to go deeper into that to get completely what is happening. Just it is only a hand waving argument I am giving for you to get a feeling for it. This is not the final. Please remember, it is only a hand waving argument. Some points which I am giving you to get the concepts clear for you. If you want to detail understand what is happening, you must go to mathematics to understand. Let us not do that, and I'll give you conceptually what is happening. After first 90-degree pulse, what happens? Let us say I have 2 spins coupled, A and X, weakly coupled. A will be a doublet, X will be a doublet. They are coupled into, and each of them is a doublet because there is a J coupling. As I told you, J coupling is a requirement for Cauchy. If the spins are not J coupled, you will not be able to do Cauchy experiment. So let us say spin A evolve under the influence of chemical shift, T2 relaxation, magnetic field inhomogeneity, and scalar coupling, all which I told you here. It evolves under various parameters: chemical shift, relaxation, magnetic field homogeneity, of course, coupling, which I did not mention here. Everything will be present. The spin A start evolving with under the influence of all these parameters: chemical shift, magnetic field inhomogeneity, all the four contribute to this. During the evolution time T1, spin A will be precessing at the resonance frequency of nu A. Because remember, chemical shift nu A and nu X are different. So nu A has its own resonating frequency or precisional frequency. Nu X has its own precisional frequency. They are different. Okay. But since I am taking only A and X as the two spins, A spin will precess, I denote as nu A. Precisional frequency of A is nu, and I call it nu A in T1 period. Okay. Now, what happens to second 90-degree pulse? It again transfers part of the magnetization of to the longitudinal axis, which I said earlier, and leaves part in the transverse plane, evolving at the same frequency nu A. Remember, already magnetization is the transverse plane. Spin A is evolving under the influence of chemical shift, J coupling, magnetic field, inhomogeneity, scalar coupling, everything. Second 90-degree pulse transfers part of this back to Z axis in the longitudinal axis and leaves part of the spins, part of this magnetization in the same transverse plane. What is happening? Their precision frequency is still nu A. Okay, they are evolving at nu A frequency only. That is not changed. Okay, but it also converts part of spin A magnetization to spin X magnetization. That is a polarization transfer effect. This is called polarization transfer, effect of polarization transfer. What happens is the spin A, in addition to spinning, precessing about its own frequency, during the period of evolution, it gives part of its magnetization to spin X. That is a very interesting thing. You see, it gives part of its magnetization to spin X by what is called polarization. This effect is called polarization transfer. Now, in the effect, what happens is the precision frequency of the spins during T1 and T2 evolution period is no longer same. What happens in the T1 and T2 period? The precision frequency of spins are not same, because it is not only remaining, it is not remaining as individual nu A and nu X. Individually, nu A was precessing at the nu A frequency nu A. It gives part of the magnetization to nu X also, and part will go back to Z axis. The effect is, you can't say during both the time period the precision frequencies are same. They are not same. They are different. So the 2D spectrum, then what happens? Because it gives the magnetization at in the T1 period to X also. In the X, in the detection dimension, what happens? X will have frequency of its own precision frequency plus the frequency obtained because of spin A. So it will be appearing at two frequencies, one at nu A and one at nu X. What happens to the precision frequency of nu A? That magnetization is given to X. That's what happens. So we get peaks at the precision frequency of nu A, which is in T1 period nu A, remains same in the T2 period also. That is one signal. We also get a peak whose precisional frequency is nu A in T1 period, which has given its magnetization to X, whose precision frequency is nu X in the T2 period. So in the T2 period, we have peaks whose precision of the magnetization evolution periods is not different. As a consequence, these frequencies are different. We get frequencies depending upon whether they have the same frequency as it given magnetization to coupled spin. Now, what do you mean by giving the same whose precision frequency has not changed, which remains same? Part of the magnetization went back to Z axis, it remains same. It has given magnetization X spin. That will appear only as nu A and nu A. They are called diagonal peaks. The frequencies which remain same both in T1 and T2 dimensions, both in evolution and period and detection period, if the frequency remains same, that comes as what is called a diagonal peak in Cauchy. In Cauchy, the diagonal peak comes where the precessional frequency of the spin both in T1 period and T2 period remains same. On the other hand, the precessional frequency of nu A, which is transferred to nu x, appearing as nu A and nu x also together at nu x in the T2 dimension, that comes as what is called a cross peak. The cross peak comes because of polarization transfer of A spin to X spin. This happens because of J coupling. So when there is a J coupling, there is a transfer of polarization. As a consequence, the precessional frequency of X is also seen at the precessional frequency effect. They appear as nu A and nu X, both the frequencies. They are called cross peak. It is called a cross peak. And when the frequency of nu A remains same in both the dimensions, it's a diagonal peak. When the precessional frequency of A is nu A and also nu X, this is a cross peak. Okay, this is for A spin. What about the X spin? Identical, same explanation. When the precessional frequency of X remains same in T1 and T2 dimensions, it gives a cross diagonal peak at nu X frequency. If nu X also has given its magnetization to nu A, see similar argument, then in the 2D spectrum at the nu X frequency, you can also the effect of it, the nu A precession frequency also you see. You understand? The 2D spectrum, you get diagonal peaks whose frequency remains same in both the dimensions, whose frequencies are different in both the dimensions, come as cross peaks, which is true for A spin, which is also true for X spin. And I took the example of two weakly coupled scalar, weakly coupled two spin system to understand this. I suppose you got the point now. Now, let us try to understand the general interpretation of a two-dimensional spectrum. It could be Cauchy, Nosy, Rosy, anything. I'm just, with this understanding, let us see what is a peak. I was telling you about frequency nu A in both dimensions, nu A, nu X, nu X, nu A, nu X, nu X, all four possible combinations we discussed. Now, let us say, I have done a 2D experiment. Take Cauchy, no problem, any experiment. For understanding purpose, we will take Cauchy. This is the experiment of 2D which we have done. And I see a cross peak here. Is the peak is on diagonal? This is not on diagonal. Okay, there is no diagonal peak. That means if you want to interpret, if you go in this dimension, at F1, this precessional frequency is 20 Hz. In the F2, its precessional frequency is 80 Hz. So, what do you understand from this? This signal here is evolved in the T1 dimension at a frequency of 20 Hz. But in the T2 dimension, it has evolved at 80 Hz. I suppose you are understanding me. Because of the mixing time, the magnetization of this is transferred to this, which was evolving at 20 in the T1 dimension. As a consequence, the peak which was evolving at 20 Hz in precessing at 20 Hz, let us say, in the T1 dimension, has given its magnetization to coupled spin, and as a result, it is giving a peak at 80 Hz in the T2 dimension. This is what you have to understand. Okay, so this spin has given magnetization to another spin, and this spin has its own frequency retained. In the T1 dimension, it is always 20 Hz, whereas in the T2 dimension, it is 80 Hz. This is how you have to interpret. You have to do like this. So, if I want to see what is the peak precessional frequency of this peak or this spin or this magnetization, I will say in this F1 dimension it is 20 Hz, and in the F2 dimension it is 80 Hz. That's the way you have to interpret a 2D spectrum, any 2D spectrum. Now, let us say I have a peak here. Remember, now the peak is on the diagonal. Okay, on the diagonal now. What do you understand from this? There was a peak which was precessing at 20 hertz in the F1 dimension, and its frequency is unaffected and it has not given magnetization to any other spin. So it continues to remain at 20 hertz precessional frequency even in the F2 dimension. That means it has no coupled partner to give its magnetization to other spin. As a consequence, this peak comes as a diagonal peak. When the diagonal peak is there, take a line here, take a line here, both the frequencies are same. Understand? Now this peak is coming at 20 ppm, 20 hertz in the F2, 20 hertz in F1. So this frequency remains same in both the dimensions, and it has not given energy to any other peak in this dimension or in this dimension. As a consequence, it has no coupled partner. So it is a diagonal peak. That's what you have to understand. Now let us consider a situation like this. I have two peaks. There was a spin which was precessing at 20 hertz in F1 dimension. During the process of mixing, it will give its magnetization to another one, okay, which is going to be spinning at 80 hertz in the T2 dimension. You understand now? You have to see this has a frequency of 20 hertz in the F1 dimension. This has a frequency of 20 hertz and 80 hertz both in the F2 dimension. How? Look at it. In this dimension, you have only one peak which corresponds to 20 hertz. But this is a T2 dimension. T2 dimension is one peak here at 20 hertz. There's another peak here at 80 hertz. That means this spin, which was precessing at 20 hertz in the T1 dimension, has given its magnetization to another spin which was spinning, which has its precision frequency at 80 hertz. As a consequence, you can see it has retained its frequency and also gives part of its magnetization to another spin, which has evolved at 80 hertz in T2. I hope I made this point clear for you. Let me repeat. There is a spin which is precessing at 20 hertz in the T1 dimension. In the evolution period or mixing period, what happens? During the process of this, it will give part of its magnetization to another spin which is at 80 hertz in T2 dimension. At the same time, it has retained its frequency also in the T2 dimension. So if you analyze this spectrum, in the F1 dimension it has its 20 hertz, in the F2 dimension it has retained its frequency, also gives magnetization to another spin whose frequency is 80 hertz. That means, what do you understand from this? This spin is retaining its own frequency in both the dimensions, giving a diagonal peak, and also it is giving a cross peak for the spin which is coupled to through scalar coupling. Now I will tell you this is coupled to this. I have to find out this diagonal peak for this. We will see in the next Cauchy spectra. But for interpretation, you understand this spin has given magnetization to another spin which is resonating or precessing at 80 hertz in the T2 dimension. This is how you have to interpret any 2D spectrum. I have taken an example of one simple thing. This spectra, beautiful spectra taken from Keeler's book. You can see that. So now I know how to understand, how to interpret it. I suppose you understood everything. Now we'll go to this class. You understood in depth about 2D sequence, especially number of possible 2D experiments, what we can get out of which. And then especially I took the example of a Cauchy two-pulse sequence, how the magnetization evolves, what happens to magnetization, how one spin precessing at a particular frequency in the given period transfers its magnetization to another spin during the evolution period and mixing period, and how the peaks will appear on diagonal peak and cross peak. Diagonal peak is the one where the spins retain its precision frequency in both the dimensions. Cross peak is the one the spin gives its part of magnetization to another spin which is coupled to it. As a consequence, this frequency comes in a different frequency in the T2 dimension. So that is a cross peak. So we took several examples and see how to interpret a 2D spectrum with only 1 or 2 bit present. And this interpretation is invariant for any type of 2D experiments you do. Okay. So with this, I'll stop here. We'll come back and start with the analysis of the 2D spectra in the